Okay, well, it's a great pleasure to be here. Thank you so much for showing up. And so today I'm super excited to share some of the recent developments in my own field. So as Liang, thank you for the nice introduction, Liang, described, I'm a theoretical cosmologist. My research is on the beginning of the universe. I think about what happens right in the first few instants of the universe. And today what I'm going to try and convince you of is these recent developments of our understanding of where everything in the universe comes from. And where everything in the universe comes from, we think, is from quantum mechanical fluctuations in the very fabric of space-time during the first few instants of the universe. So this is a fairly outlandish claim, I realize that. But I'm hopefully going to convince you of is that we're really building up a body of evidence which really supports this picture that everything in our universe really did arise just from quantum mechanics. But before I begin, I just want to acknowledge actually your support. The only reason that we're even able to think about these questions is from support from you. So my research in particular is supported by NASA and the Department of Energy, and of course these are government agencies, so these are your taxes. So this is your tax money hard at work. Thank you very much. So, okay, so what I hope to, so basically the basic question that we're trying to understand is, where did all this stuff come from? So this is an image from the Hubble Deep Field. So this is basically the Hubble telescope sitting there staring out at one point in space. And so the size of this field is about 1 millimeter square, held at about arm's length, right? So that's how big this field is on the sky. Okay, so where did all this stuff come from? So in order to describe where all this stuff comes from, I have to tell you about the Big Bang Theory. And so many of you probably know about the Big Bang Theory inside of it. So when I was in graduate school, this show actually first started when I was a graduate student about 12 years ago. And when I was in graduate school, we were all very excited, right? Because we were all excited. Here was this TV show that was going to be about us physics graduate students. And so all my friends, we all got together to watch this thing, and it was just too much. It was too close to home, and we just couldn't do it. So of course, the real Big Bang Theory is a thing, right? So the Big Bang Theory has the universe beginning in this Big Bang and expanding ever since. And so to really tell you about the quantum origins of fluctuations, I need to give you a little bit of a primer on what exactly is this Big Bang Theory. So the things to know about the Big Bang Theory. So the Big Bang Theory has that the universe is expanding, and it began with a Big Bang in the beginning. So this expansion means that in the past, the universe was hotter and denser, and structure in the universe, so galaxies, stars, etc., are formed from gravitational collapse. So things started out small in the past and grew into the future.
Question.
Yeah?
Why number 3?
Why number 3?
Well, I have the fundamental question you help me answer.
Okay.
Is there gravity with gravitons, or is it just negative curvature of space?
So those two things, that's two sides of the same coin.
Repeat the question.
Oh, so the question is it curvature of space-time or is it gravity? And according to Einstein, there is no such thing as gravity, there is just curvature of space-time. So if you believe Einstein, then it is just the curvature of space-time. But the whole point of this thing is that the result, that galaxies are there, they form, they were small in the past, and they grow towards the future. But that is a good question. Other questions? So please ask me questions throughout. I'm happy to take questions. I think these things are better when they're sort of more interactive, when you guys can get your questions answered. So of course, really back in the old days, people thought that the universe was eternal, right? That it was unchanging, it was static. And indeed, when Einstein first wrote down general relativity in 1916, a consequence of his theory was that the universe was either expanding or it was contracting. And back in that day, everyone knew that the universe didn't change. So what Einstein did is he added his famous biggest blunder, the cosmological constant term, in order to obtain a static universe. A few years later, in 1922, this guy, Hubble, determined that the universe was indeed expanding. by observing distant Cepheids in distant galaxies. And what Hubble observed is he found that all these galaxies out there in the universe seem to be receding, seem to be disappearing, going away from us at a rate that was proportional to how far away they were. So the further away the galaxies were in the universe, the faster they appeared to be receding. And the only theory that makes sense is that the universe, that this implies, in fact, that the universe is expanding. So the consequence of the universe expanding, of course, is that if you run time backwards, things that are far apart today were actually closer together in the past, right? So you imagine running the clock backwards, so the distance between galaxies, so the expansion of the universe means that the galaxies aren't actually moving through space, it's the space in between them that's actually expanding. So as the universe expands, there's space being created. So as you go back in time, the space is going away and things are getting closer together. So the universe was denser in the past, and this is a direct result of the hot Big Bang cosmology. So all these galaxies, as we go back in time, get closer and closer together. And at some point, there wasn't enough room for there to be individual galaxies. And so the universe, according to the Big Bang theory, would have started out as this tiny dot. And indeed, you know, the whole name, the Big Bang theory, was actually a pejorative. It was actually made fun of by the proponents of this theory. They were made fun of for saying, oh yeah, the universe began in this Big Bang. How improbable is that? And so it turns out that this is actually probably what happened. So the other thing you'll notice is that as you go back in time, as you compress things, they get hotter. So as you take a gas, so you're probably familiar with pumping up the tire on your bicycle, that pump gets quite hot as you compress gas. So as you go back in time, the universe gets hotter and hotter. And so at some point, all of the matter in the universe would have been blended together in this sort of hot, turbulent mess. And all this matter sloshing around would be radiating, and the hottest, densest parts of this sort of big, dense blob would be radiating the most. So the further back you go, the hotter it gets, and so this is an actual plot of the temperature. So the temperature today of the universe is roughly a couple of Kelvin, but as you go back in time, it gets hotter and hotter and hotter until you get really, really close to the Big Bang, where it gets up to basically the Planck temperature. And so one way of looking at that is as you go back in time, the temperature goes up, or if you start from early times, as the universe expands, it cools down again. And so here we are today, sitting out here at so this is 14 billion years after the Big Bang singularity. So what this means is that at some point in the early universe, the temperatures were just too high for there even to be atoms, right? So at some point, the radiation has so much energy that it just basically ionizes any atoms that are there in the universe, and the universe eventually just becomes this ionized plasma of electrons, photons, and nuclei just floating around. So when the universe is in this ionized plasma, the mean free path of a photon, so the mean free distance that a photon can travel before it hits an electron, is very, very short. And so at this point, the universe actually becomes opaque, and we can't see, you can't see anything beyond this point. And so the radiation, so as you imagine now running the universe forward again, the radiation that's emitted from this transition is what we call the cosmic microwave background. So radiation from the hot Big Bang itself is actually the CMB radiation. So basically, as the universe expands, this radiation remains, and it just travels through the empty space. So it travels through the empty space around all the galaxies and travels across the universe today. And so this radiation has been traveling across the universe for, well, so I don't know what, my slide has gotten a bit messed up, but it's been traveling across the universe for 13.7 billion years from the hot Big Bang surface all the way to us today, where we now observe it in our telescopes. Okay, so please ask questions about anything I'm talking about. Mm-hmm. So this radiation, the wavelength has been shifted. Yeah, exactly. So from when it was released, so it turns out the wavelength of the radiation is stretched by a factor of 1,000. So the universe, from the time at which the radiation was released, has expanded by a factor of 1,000. So the universe is 1,000 times bigger than it was when the universe was too hot to have atoms than it is today. And so the temperature back here was about 3,000 Kelvin, and today it's about 3 Kelvin. Yeah. So the wavelength of this radiation has been stretched by that factor of 1,000. Yeah.
Did we ever image one of those first stars that you had on there?
Yeah. The image I showed on the first slice is actually the Hubble Deep Field is actually galaxies that are about 1 billion light years away. So you may have seen, so there's now newer images. So there's the so-called Hubble Ultra Deep Field, which goes back, so actually that's actually 13 billion years. So those galaxies and the Hubble Deep Field are 13 billion years ago. And then the Ultra Deep Field goes back about another billion years. So yeah.
What's the Dark Ages? Isn't that contemporary time?
Yes. Almost, right? So we're somewhere back, yeah. So the Dark Ages, so as I described, our theory of Big Bang cosmology has, all the structure grows gravitationally. So in the far past, the fluctuations were so small that galaxies hadn't formed yet. So there were no collapsed objects, there were no stars, and so there was no light, and so this is referred to, so after recombination, all that there is the microwave background radiation streaming through a reasonably smooth universe, right? And then slowly the structure starts forming as matter collapses onto overdense regions. Yeah.
Thank you.
Yes?
You said the universe temperature is 3 Kelvin, right?
So the temperature of the universe is 2.762 Kelvin. So that's the temperature of the microwave background. So so essentially the sort of a cute way of thinking about the universe is sort of like an inside-out star, right? So when we look at our sun, what we're seeing is light that last scattered about 8 minutes ago, right? So we're seeing the surface of the sun is 8 light minutes away. So the photons that are leaving the surface of the sun left that surface 8 minutes ago. The light from the Big Bang, on the other hand, is the shell of radiation that surrounds the Earth, which is 13.7 billion light years away from us. So in some sense, our universe is sort of this, weirdly, this inside-out star.
When did the first stars form after the Big Bang?
So the first stars formed roughly about 1 billion years after the Big Bang. So 500 million to 1 billion years after the Big Bang. Yeah. So most of the age of the universe has been in since the first stars actually formed. Yeah. Okay. So what does the CMB look like? So it turns out you can actually see the CMB on your TV. Well, at least you can. You could have seen the CMB on your TV back in the old days. So the CMB today is approximately 1% of the noise, so just the white static noise that you see when you turn on your TV screen. If you just detune your TV and you see this noise on it, about 1% of that is actually the microwave background photons. And yeah, so a little caveat. At the last minute, I had to convert my presentation from Keynote to PDF. So I apologize. This was supposed to be a movie doing that over and over again, but the movie didn't quite get converted. So I apologize for that. So of course, famously, this 3-degree Kelvin background was actually discovered in 1965. So this CMB background was actually predicted as early as 1948. So they knew, back in the 40s, that the sort of smoking gun prediction of the hot Big Bang, so at the time there were two competing theories for the origin of the universe. So in one theory, the universe was really eternal. It was really, it was the so-called solid steady state model where matter was just sort of continuously created, the universe was expanding, but at every point in space, you were sort of continuously violating conservation of energy. So you were continuously making energy. And then in the other theory, you had a hot Big Bang, and the universe had been expanding ever since. And so in the 40s, I think it was Gamow, realized that the hot Big Bang theory would predict this background radiation called the CMB. And so it turned out it was discovered almost accidentally in the 60s by Penzias and Wilson. So Penzias and Wilson were working for Bell Labs at the time, and they were trying to understand the source of this pesky microwave background that they were seeing in this giant horn antenna. And it turns out at roughly the same time, Dickey and Wilkinson, so this is actually, Bell Labs is quite near Princeton University, so over at Princeton, Dickey and Wilkinson were actually actively looking for this thing. And so these two basically scooped the Princeton team to discover the CMB. And so they received the Nobel Prize in 1978. But as a microwave background experiment, this thing is actually really over-designed. And so the microwave background was detected subsequently to this, basically in a box off the roof of the Princeton physics department. And every time we sort of find out something about the microwave background, it makes the front page of the New York Times. And so this is May 21st, 1965. The Penzias and Wilson measurement, here it is on the front page of the New York Times. So this is really kind of a big deal. So what convinced them that this really was cosmological in origin is what they observed the same intensity in all directions. So famously, they turned their antenna every which way, and they found that they were receiving exactly the same intensity of radiation from every direction. And so it turns out if this had been the end of the story, this would have been a complete disaster for Big Bang Theory. Because after all, where would galaxies have come from? Because this microwave background is essentially a snapshot of the universe when it was just 380,000 years old, right? So this is like taking a photograph of the state of the universe just after the Big Bang. So if the universe really had been completely smooth, then subsequently there'd be nothing, right? The universe would just be big and empty and completely smooth, this bath of photons at 2.72 Kelvin, and there would have been nothing else. So it turns out that over time, we made more and more accurate measurements that with better resolution of the microwave background. And so in 1992, the COBE satellite first detected the fluctuations in the microwave background. In 2003, the WMAP satellite made an even more precise measurement. And today, we have these absolutely exquisite measurements from the Planck satellite, which have now measured this. So you can see what's basically happening here is that the telescope that they're imaging the sky with has better and better resolution. So they're able to pick out the finer and finer features of these little bumps and blobs in the temperature. So this is a plot now of what's been done is they've subtracted out this 2.762 Kelvin, this so-called monopole, and what's been plotted here is actually the deviations away from this average temperature. And so again, so every time, as I said, every time we make a new measurement, the New York Times puts it on the front page. And so this was the one for the first Planck release, which is March 22nd, 2013, which is about 5 years ago today. So there are small variations in this temperature across the sky. So as I said, I think I put this wrong on one of the slides, but the average temperature is 2.762. I think there's a 6 missing here. And then the fluctuations turn out to be about 1 part in 10,000. So it's this incredibly smooth background with these really, really tiny fluctuations. And these tiny fluctuations, what they correspond to is little regions of space where the plasma, so there's a plasma of electrons and photons, it's little places where the plasma is just a little bit hotter or a little bit colder. So these are basically density fluctuations in the primordial plasma. And as I mentioned, these density fluctuations that cause these fluctuations in microwave background temperature, these are the things that provide the seeds for the subsequent structure formation. So here's this is basically data from the Planck satellite, and this is a time of 380,000 years after the Big Bang singularity. So if you run the clock forward a little bit, and you use this to start a simulation 500 million years after so you can evolve these initial conditions, you evolve them forward, and you do a simulation where you put in 10 billion particles in a giant box, and you let gravity. So this is 500 million years after the Big Bang, and then you run it forward a little bit. So you run it forward to 130. So this is 1.3 billion years after the Big Bang. A little bit further forward, you see that this cosmic web of filaments and structures begins to form. And so this is what the cosmic web looks like today, 13.7 billion years after the Big Bang. And it turns out that this is almost perfect. It gives you almost exactly the right galaxy distribution to match on to what we actually observe in our universe. And so basically the Big Bang theory, as I've described it, is really this nice, it's really this beautiful theory. It really predicts everything we see from a point, so from the point where the microwave background is released all the way to today. The Big Bang theory just works beautifully. But it really doesn't, so the Big Bang theory, it turns out, has a bunch of problems when it comes down to thinking about what happened before the microwave background was released. So the question is, what happened, what's supposed to happen right at the Big Bang? So it turns out, theoretically, there are a bunch of problems with this hot Big Bang model. And it turns out that, as I described earlier, the uniformity of the microwave background is actually a big problem theoretically. So theoretically, the fact that we see exactly the same temperature at all points on the sky to 1 part in 10 to the minus 4 is a really, really big puzzle. And so the reason this is a puzzle is that, as you know, light only travels at a finite speed. So light, it turns out that what I've done is I've unwrapped that sphere and I've just put it onto this plane. So, and I apologize for my text getting a bit messed up here. But since the Big Bang singularity, so now what I'm plotting here is time and space, so time is going forward. And so as time goes forward, you see photons propagating out from the singularity. A photon can only propagate a finite distance. So this region, so the region that's in causal contact with the hot Big Bang surface is only this size, right? So if you started off with some initial condition here and propagated it forward, then only regions within this horizon have had time to actually have a conversation and agree that they're all going to be the same temperature, for example. So this would be fine if, when we look back, we could only see this whole region, right? If we could only see this region that was in causal contact, then everything would be okay. But it turns out that our past light cones, so the region of the last scattering surface that we can see, turns out to encompass many, many of these horizon-sized patches. So it turns out that our microwave background sky is actually composed of 40,000 causally disconnected patches. So these 40,000 apparently patches of the sky that have had no time to remember, you have last scattering, then the photons just propagate to us without talking to each other. They don't have a chance to have a conversation, and all of these 40,000 regions somehow had to decide that they were going to have exactly the same temperature, right? So that's like, me running a bath at my home in Urbana, and then my parents back in New Zealand running a bath back in New Zealand, and then somehow our baths are miraculously exactly the same temperature without us having a conversation about it, right? So that's a bit weird, and so from a physics standpoint, it's incredibly strange that these apparently causally disconnected regions, so by that I mean there's been no time, there's literally no time for this patch of the sky over here to tell this patch of the sky over here that it was going to be 2.762 Kelvin, right? And so, there's this sort of open question in physics as to how is this the uniformity of the microwave background consistent with causality, which is really a fundamental sort of notion in physics. And so, of course, one way that it's consistent is that maybe God just painted down. So maybe that in the Big Bang singularity, God just painted down the spectrum of fluctuations, and that's what it is, right? But as scientists, that's somehow unsatisfying. And so we'd really like to have some kind of theory which actually accounted for all these surfaces having the same temperature. Yeah.
Is it possible that the different regions are possibly entangled with each other?
Yeah, but you'd have to, so the question was, is it possible that the different regions are entangled with each other? And it is certainly possible. And in fact, that's actually what our theories predict. But entanglement is still causal, right? You still have to have a causal mechanism to send, if you like, one entangled qubit here and one entangled qubit here. But according to this picture, there's simply just no time, right? There has been no time for a signal to propagate from here to here. So it's still, so yes, they could be entangled, but you need some theory to actually predict that. Yeah?
Quantum mechanical operations don't involve time. They don't have a preferred direction. So isn't it possible to have this contact by going back into the past?
Well, there is no past, because this is where time began, right? So time began here. So there is no past beyond this point. So, because, I mean, this is a singularity, right? We don't know, so physics breaks down basically at this point. So if we assume, okay, that something happens and then physics started to make sense, right? Then going forward, so assuming, the laws of physics hold from just above this point onward, then somehow whatever set up the initial conditions here had to set it up in this very, very particular way so that every point in the CMB had exactly the same temperature to 1 part in 10,000. And so that's the problem. There's a question over here somewhere. Yeah?
Weren't they all together at the Big Bang?
Exactly. So it turns out that the solution to this problem is, so at the Big Bang we can't say anything useful. So what we do is, what we postulate is that in fact the universe underwent a period of extremely rapid accelerated expansion right after the hot Big Bang. So right after the Big Bang, you have this period of extremely rapid acceleration where a tiny patch of space essentially becomes the entire universe. So a small patch of space gets expanded by a factor of e to the 50, which is 5 with 21 zeros after it, in as little as 10 to the minus 36 seconds. So this is the theory of inflation. So this is how we solve this problem, is precisely by just making the entire universe in one little patch. So taking one little patch of the universe and just stretching it over the entire sky.
So does that mean it's expanding faster than
Yeah.
Is that like an ad hoc?
No, so this is a completely valid solution of Einstein's equations. So yeah, so let me get to that in just a moment, and I'll try and clarify. So often we say that it is traveling faster than the speed of light, that it's expanding faster than the speed of light, but that's actually not a very sensible, it actually turns out that it's just not a sensible statement. But just to give you an idea of the scales involved, so a patch of space is expanded by a factor of at least 5 with 21 zeros after it, and as little time as, so I've written out all the zeros just for dramatic effect. So this is 36 zeros. So in as little as 0.36 zeros 1 second after the Big Bang, a region of space that's the size of a proton, so this is 10 to the minus 15 meters, is stretched to something about the size of the Earth, right? So the Earth is around 10 to the 9, so 10 to the 15 to 10 to the minus 15 to 10 to the 9 is 10 to the 24. So this is roughly the scales that we're talking about. Another way to think about it is something about the size of a strand of DNA being stretched to something the size of the solar system. So in this really, really short amount of time. So what's actually nice about the theory of inflation is what it does is, so the hot Big Bang creates sort of a baby universe, but we know that babies are messy things, right? They can be bumpy, they can be lumpy, and so what inflation does is it just takes out all these bumps and lumps and it just stretches them out, and you see we started off with that really, really lumpy universe, and as we stretch it and we stretch it and we stretch it and we stretch it, all those lumps and those bumps are gone, and in the end we're just left with this perfectly smooth and homogeneous universe. And we do this really, really fast, and so so how does this work? So usually the expansion rate in the sort of post-inflationary epochs is actually quite slow compared to light. So as we're sitting there with our telescope and we look out, we can see, so as we look further and further back, we can eventually see the entire universe. During inflation, the expansion actually outruns light. So if we're trying to look at this galaxy after 1 year, after 2 years, the galaxy has just gotten so much further away that our, whatever light that we're trying to see is never going to reach us in time. And so sometimes you'll hear inflation described as superluminal expansion, but really that it's sort of a nonsensical it really doesn't make sense to assign expansion to a speed, because remember, in Einstein's theory, to compare a speed with someone, you have to compare something at the same point at the same time. And there's no way you can compare. So if you have a meter stick which is expanding at the speed of light, you can't compare one end of that meter stick with the other end of that meter stick. So there's no way that this really corresponds to a velocity in the usual sense of the word. But if you measure the speed at which these two ends are receding from each other, that does exceed the speed of light. Yes?
Well, did this inflation last in a specific period of time, or is it still going on?
No. So that's a very good question. So currently the universe is inflating today, but for a very different reason. So it's inflating today because there's dark energy in the universe. So maybe you've heard of this mysterious dark energy stuff. So that's kind of exactly the same sort of thing, but it's at a much lower energy scale. But inflation, as I mentioned, lasts only this 10 to the minus 36 seconds. So it turns out that the inflation, so this is as short as inflation can last. So I put in the shortest number here just for sort of dramatic effect. But inflation could have lasted as long as, I think, it could have lasted about as long as a minute. Yeah.
Has there been an experiment proposed to duplicate in some small, vanishingly small way, this kind of inflation today?
No, we can't do it. All we can do, and so as I'll describe, so let me get to the tests of it, because I know that I'm standing down here and I'm making outrageous claims. Like, these are crazy, right? You probably think I'm a crazy person, and you can't believe that your tax dollars are paying me to do this crazy stuff right now. But let me get there. I'll get there hopefully. So the way this solves, so it basically solves this so-called horizon problem. There's a whole bunch of other problems which I didn't mention with the hot Big Bang. Is it takes this tiny patch of space and it just stretches it over the entire past light cone of our Earth. And so now essentially a region of space that was in causal contact. So you imagine before inflation there was time for all this bit of space to establish thermal equilibrium, decide that we're going to be the same temperature. Inflation happens, and then suddenly this region that was in causal contact is now swept outside the horizon and is now not in causal contact today. So regions that are not in causal contact today were in causal contact in the past, according to this theory of inflation. And so sometimes you'll hear this described as inflation alters the causal structure of space-time in this kind of profound way. Okay, but if this was all inflation did, it wouldn't be very good, because we know we have galaxies, we see these galaxies, and we wouldn't be here. So inflation is stretching these microscopic scales. So as I told you, it stretches this proton to the size of the Earth. But we know that small things are governed by quantum mechanics. And so basically it's taking this little region of vacuum here and making it huge, right? But the vacuum is quantum mechanical. And here's a picture of the quantum vacuum that I found. Apparently the quantum vacuum is actually a thing. But really, so this is a simulation. In fact, so this is a simulation of quantum chromodynamics. So this is the theory of the strong interactions. So these are, I think what this turns out to be is quark-antiquark pairs popping out of the vacuum and popping back in. So these are fluctuations in the energy density of the vacuum due to just quantum mechanics, right? So the vacuum isn't just a boring place with nothing there. It's really quite this lively thing with stuff popping in and out of existence like this. And so why can this happen? Because you remember that, well, maybe you remember, maybe you've learned this at some point, that there's these things called the Heisenberg uncertainty relations. And so you can violate basically conservation of energy provided you do it over a short enough time scale. And so what inflation, because the inflationary expansion is so rapid, what happens is that these little particle-antiparticle pairs pop into existence in the vacuum, and then the expansion is just so quick that they get ripped apart and they become actual real particles once they're separated by this sort of acausal distance. So basically these quantum mechanical fluctuations, what they do is they induce variations in the energy density. This energy density, this enormous energy density is driving this period of inflation. And so when you make these variations, you make this energy density fluctuate, what happens is that you make some parts of the universe stop inflating a little bit earlier than other parts. So the parts that stop inflating a little bit earlier, they have time to expand and cool a little bit more than the regions that stop inflating a little bit later. So the regions that stop inflating later start the hot Big Bang later, and these have less time to expand as we see them today, and the universe correspondingly appears hotter and denser in these locations. So the end result is a very slightly lumpy universe at the end of inflation. I mean, these are still quantum mechanical fluctuations, and so the fluctuations that you get at the end are still small, but as I mentioned, we only want small things. We only see small fluctuations in the microwave background, and so that's all we want to make. Yes? Sorry? Yeah, so that's what I'm paid to do. So we don't actually know. So inflation, we know that, we don't know. So nothing, so the answer is that we don't know what causes inflation. We do know, we are able to write down theories that generate inflation. And so a theory that looks very much like, so most of you hopefully have heard of the Higgs boson. So a theory that looks like the theory that gives mass to everything in the universe actually would do a pretty good job of inflating the universe. But it turns out that the parameters, it turns out that if you try and use the Higgs boson to do this, it doesn't quite work properly. Yeah?
So you mentioned that quark-anti-quark pairs that
yes.
the early universe expanded and became particles.
Yes.
So if that were the case, then why is, I know it's an unresolved problem in physics that there's more quarks than anti-quarks.
Yeah.
So would that shine any light in that problem?
So yeah, so this is another thing that I try and think about. Yeah, so the question is, why is there more matter than antimatter? So naively, you think that if you started off with nothing and you just make particles and antiparticle pairs, somehow you have to make more particles than antiparticles. And so it turns out that the laws of physics are mostly symmetric under replacing particles with antiparticles. And so it turns out that you have to do some kind of funny things, which are kind of fun to play with, in order to get this to happen. But you can actually do it, you can do it during inflation. So inflation, the fluctuations that seed the microwave background also could generate matter-antimatter asymmetries. Yeah. There was another question. Oh, there's a question up there. Yes? Why can't we rewind time past the Big Bang? Well, if you have a way to do that, I'd love to hear about it. But currently I don't have a time rewinding device. But we essentially, the reason we can't see past the microwave background is like on a cloudy day, the reason you can't see past the clouds, right? You can't see, so the surface of the cloud is the last time the photon scattered before coming to your eye, right? So all you can see is the surface of this cloud on the sky. And so that's like the last scattering surface of the microwave background. It sort of puts a screen there that stops us seeing beyond. But it turns out that with gravitational waves, potentially we could see the beginning of the universe, and that's hopefully what I'll get to if I hurry a little bit. Okay, so basically these lumps, as I mentioned, evolve to form the C and B, and then 13 billion years later, large-scale structure. And it turns out that all of the physics that takes us from here to here and here to here is actually quite simple, and we know it quite well. And so yeah, so is this for real? Are we really the result of these quantum fluctuations? So we can actually learn about these, we can actually learn about inflation, and we can test these ideas. Because we understand how to go forward, we can essentially make measurements of large-scale structure in the microwave background and then try and see if it matches our predictions from inflation. So because these fluctuations during inflation are generated quantum mechanically, so quantum mechanics is a statistical theory, we really have to think statistically about the fluctuations in the microwave background. And so essentially one way of sort of roughly thinking about this is to characterize the microwave sky, we basically count the blobs. And so here is this map from WMAP. And as you can see, it has a whole bunch of, if you sort of squint a little bit, it basically just looks like a whole bunch of blobs of different sizes. So you can think of characterizing this map by filtering it on different scales. So this is like wearing blurry glasses and then counting the number of big spots, the number of medium-sized spots, and the number of little spots. And if you do it and you bin it up in a particular way, you just basically write down how many spots you measure, then you see that what's called, so what you get out of this is the so-called spectrum, and the spectrum of fluctuations has this shape. And so the thing that we can actually predict is the spectrum. So we can't actually predict that there'll be a hot spot there and then that there'll be a cold spot there, but we can predict what the distribution of hot and cold spots is on the sky. So if you do this with the map, so if you do this with this map, you count the spots, and so this is actual data. This is what you get. And then just the well-known physics of inflation plus sound waves. So this is actually not a fit. This is actually the theoretical line. You can see it is just amazing. So we really understand this physics really beautifully. So this is data from, I think, 2009. If we do it with the data from 2000, so you see that the data from 2009 really gets quite noisy. Once we start looking up, large spots here are on the left, as I showed you in that little movie, and little spots are on the right. And so the reason the noise is blowing up here is that this experiment really just doesn't have much resolution on really little scales. But once we start looking at this map, you see this map now has a lot more resolution on little scales. And the data from this is just amazing. So this is now the data, this is the theoretical line, and you see it's just perfect, right? We really, really understand exactly what's going on. So it turns out the physics that generates these wiggles is just sound waves in the early universe. I could spend another whole hour talking about that, which I won't, but we really understand the physics of these sound waves, which is really beautiful physics, really, really well. So if we get rid of the sound waves, then we can access the actual predictions from inflation. So inflation essentially predicts this flat kind of featureless spectrum. But what's key about the spectrum from inflation is that it's not completely scale invariant. And what that means is that the number of spots you expect on large and small scales is actually different. So if the universe was scale invariant, it would be like a fractal, right? By looking at a picture of it, you couldn't tell what scale you were on because, if you've seen a fractal before, as you zoom in, it just keeps looking like the same thing. So inflation predicts these nearly scale invariant fluctuations, but crucially, inflation also predicts that there should be a deviation, that the spectrum should be slightly red, that there should be, and this means that you have more power, so more spots on large scales than on small scales. And this is actually now, we've detected this at almost 5 sigma. So this is data from a whole bunch of experiments, and you can see that they really prefer a value of the spectral tilt, which is different from the scale invariant tilt. Okay, but as I keep saying, extraordinary claims require extraordinary evidence. And so we're kind of lucky with inflation because it turns out there really is a smoking gun. That you can write down a number of theories that give you fluctuations, but it's really just inflation that predicts this one particular signal on the sky. And so let me, in the last few minutes, try and describe this. And so this has gotten badly mutilated, but what this said was in addition to these density fluctuations, inflation generates, so these density fluctuations you can think of as the matter fields. Whatever matter is present during inflation, the quantum fluctuations of that field, particle-antiparticle pairs, getting ripped out of the vacuum and becoming actual density fluctuations on large scales. But inflation actually generates ripples in the space-time itself. So the space-time itself in inflation actually gets these ripples in it due to the accelerated expansion. And these are gravitational waves. So inflation generates gravitational waves, and the space-time itself is ringing after, as a consequence of this period of inflation. And so this one said, how do we learn about these gravitational waves? And I apologize that this got cut. So you remember that in addition to intensity, photons also are polarized, right? So what is a photon? So a photon is a propagating electric and magnetic field. The polarization of a photon is the direction of its electric field. So here's a little movie of this. So this is a propagating photon. It propagates this oscillating magnetic and electric field. And the direction of this electric field is the direction of its polarization. So we can actually measure also the direction of the polarization of the photons that are coming to us from the last scattering surface. And so there's additional information. So this is a plot of temperature, and on top of this plot of temperature is superimposed the direction of the electric field of the photons that's received. And so polarization information is therefore a direction as well as an intensity at every point on the sky. So why is this important? So it turns out that gravitational waves make a very particular kind of polarization pattern. So density perturbations are sort of equivalent. So according to Einstein's theory, a density fluctuation is like an isotropic stretching of space. It makes volumes bigger or smaller, if you like. And these isotropic stretching of space around hot and cold spots, the polarization vector of the photons has these particular shapes. So a gravitational wave is this anisotropic stretching of space. So this is like blowing up a balloon and then squeezing the balloon, right? You don't change the volume of that balloon, but you change the shape. And that's sort of, gravitational waves you can think of as space distorting but not volume changing distortions. And so these generate these very particular patterns on the sky, and what you'll notice is that there's a handedness, if you like, to these patterns. So hot spots have a particular handedness, and cold spots have the opposite handedness. So primordial B-mode polarization in the microwave background would be a smoking gun signature of inflation. Yes? I beg your pardon? It's linearly polarized, yeah. So you can write down theories that, so I've written down theories that circularly polarize it, but yeah, in the standard theory, it's linearly polarized, yes. But this is, yeah, so this is the polarization patterns spatially on the sky. So if we saw the signature on the sky, this would be a smoking gun signature of inflation. So we've already seen the E mode. So we've already seen the polarization in the microwave background. So if you just take a whole bunch of these hot and cold spots and you stack them on top of each other, then you see these characteristic patterns where you see the polarization vectors in the cold places going round and the hot places sort of pointing radially out. And these are just, if you take all the hot and cold spots in the Planck data and you stack them on top of each other, this is what you get. And so this is what we like to say is the artist's impression of what a B-mode map might look like. And it turns out that really this map, if you transform it into these shapes, is actually mostly E-mode, but it's still kind of nice. These swirly patterns are sort of characteristic of this B-mode signal. Okay, so in 2004, at the South Pole, so you may remember in 2004, we went crazy, right? We really got excited because this experiment called BICEP 2, which is, well, they saw this. And we went nuts, right? We got so excited because this, you look at this, it has this characteristic swirly pattern. It made the front page of the New York Times. We were thrilled. This was huge. But it turns out that other things, so as I said, primordial B-mode polarization is the smoking gun signal of inflation. It turns out that intermediate galactic, so as the photons propagate to us, they can scatter off dust in the intergalactic medium, or the dust in the intergalactic medium can emit microwave photons. And these, it turns out, also mimic the same pattern. And so it turns out that it's likely that most of what BICEP was seeing in this map is not actually primordial. So we were all a bit deflated. So that was a bit sad. But it's really, this is an extremely exciting time for this field because we really are, so this is the sort of theoretical space. This is roughly theoretically as large as the signal could be was here, right? So BICEP basically saw the largest possible thing that it could see. And it turns out that that being dust means there's still some space under here for other sort of inflationary models. So different inflationary models basically predict different amplitudes of gravitational waves. So there's still lots of space, and we're really just beginning to probe this sort of interesting region. And the exciting thing about this is that if we observe B modes, it not only proves that inflation is true, it also implies that inflation is driven by some enormous energy density. And the energy is 10 to the 13 times higher than that at the LHC. So this is like comparing the energy released when you light a match with the energy released when you set off a nuclear warhead. So this is like probing nature at the highest possible scales, beyond anything we'll ever do on Earth. So really, if we do measure these things, we're learning a lot about the universe. So the search continues, at the South Pole, they've updated, so this is the BICEP experiment, over here is the SBT experiment, so a number of our faculty members here are involved in SBT. They're continuing to search for these B modes. There's a competing experiment run by the Princeton crowd in the Atacama Desert called the ACT telescope. And finally, beyond Planck, we're going to hopefully put more telescopes into space to look for this characteristic polarization signal. So let me just summarize, and then I'll take questions. But the universe, we're now pretty sure that the universe started off with a Big Bang 13.7 billion years ago. There's this theory that all the structure in the universe was produced during inflation by quantum mechanical fluctuations is in very good shape. We have very strong evidence. We have evidence that this is indeed what happens. And indeed, these extraordinary claims require this extraordinary evidence. And so to try and verify this, this really crazy theory, we're looking for these gravitational waves. And the wavelength of these gravitational waves is billions of light years. So these are gravitational waves that are spanning the entire universe. So you're never going to see these in something like LIGO.
Something like LIGO could never detect those.
So LIGO possibly, yeah. So LIGO it turns out won't detect these unless you do something crazy. And I've done crazy things, but you can, yeah. It turns out that, so LIGO, so the wavelength of the gravitational wave that you're detecting is roughly the size of the detector. So LIGO is detecting gravitational waves roughly kilometers in wavelength. Whereas the ones that are in the microwave background are these billion, so there's a big hierarchy of scales between billions of light years and a few kilometers. So the spectrum, so if the spectrum was tilted blue, so that there was more power on short wavelengths, then LIGO might have a chance of seeing something. But it turns out that most inflationary models actually predict a red spectrum so that the actual power on short distances is smaller than that on long distances. So, yeah, so a question.
Yeah, as I understand what you're saying is that matter came into existence through inflation because virtual particles were fully apart from each other so fast they
well, fluctuations in the energy density.
So does that mean they sort of existed before inflation?
So we don't know what happened before inflation. So we don't know what the state of the universe was then. Inflation pretty much erases any knowledge of that initial period. I mean, that's what inflation does, is just erases any initial lumps or bumps. But what inflation does, it doesn't necessarily generate matter and antimatter. What it does is it generates places where there's a little bit more matter than other places. So if there were no fluctuations during inflation, at the end of inflation, every point in space would just have the same amount of matter, right? And so there'd be no lumps, there'd be no gravitational collapse, because there'd be no preferred locations for matter to collapse onto. So if the universe was completely smooth, it would just remain completely smooth, right? And so what inflation does is it puts a little bit more matter here, a little bit less matter there, a little bit more matter there, right? And it does this by ripping out these quantum fluctuations. And so the density fluctuates up here and it might fluctuate down there.
So there was a spot where there was matter, then there was inflation?
Yeah, so there would have been, So it was probably, before inflation, was probably just some really hot, very, very hot, dense phase. Yeah. Sorry. Yeah.
Could you clarify if there's a connection between the difference in matter and antimatter and inflation?
Is there a difference between matter and antimatter and inflation? There's a.
We have more matter than antimatter, it seems.
So there are theories that connect these things together. So you can write down a theory where the fluctuations that you produce during inflation also make more matter than antimatter. This is a possibility, but most people, so the origin of the matter-antimatter asymmetry is the accepted origin for the matter-antimatter asymmetry is more likely to do with the physics of neutrinos. So actually the physics that Liang works on is actually more likely the origin, in most people's mind, of the origin of the matter-antimatter asymmetry. Yeah, there was a question further back, I think. No, over here, yeah.
So, your graphs showing the background radiation predictions and the data are just gorgeous, right? I mean,
Oh, yeah, well, they're not my graphs. They're,
right. But what about the fact that you could get blindsided if dark energy is in some, or is it you kind of compartmentalize that problem?
yeah, so dark energy, yeah, so so the question is, so my interpretation of your question is our misunderstanding, or our lack of understanding about dark energy, could that jeopardize our understanding of the microwave background? The answer's likely no, because in the early universe, when the microwave background was forming, dark energy just wasn't important. So dark energy is this component of energy density, which as the universe expands, its energy density doesn't go down, right? So whereas matter and radiation, so you take a box of dust, as you double the volume, the energy density goes down by a factor of 2, because you've just got all these, you're not making any more particles of dust, and so but you're doubling the volume, right? So as the universe expands, radiation and matter dilute, but dark energy doesn't. So in the far past, there was a really tiny amount of dark energy, which is basically irrelevant for the physics of the microwave background. And what's relevant is then how the universe evolves from when the microwave background was released to today. So dark energy is extremely important for getting, so what dark energy does is it gets the peaks in the right place in the microwave background. But it doesn't necessarily affect the physics as much as you might think. Yeah. Yeah.
So light that's reaching me right now is unpolarized. I need an axis or some physical phenomenon with an axis to polarize.
Yes.
Where does this polarization come from?
So it's polarized. It's polarized because it's essentially when unpolarized light scatters off an electron, the line of sight is the thing that is choosing the axis. So if you imagine you have an electron sitting here and here's an unpolarized stream of photons comes in, and you're standing here watching these photons scatter off, then the component of the radiation, the polarization that is parallel with the outgoing polarization will be lost, right? So why is this important? So if you imagine it, so this is it coming from the left, this is it coming from the top. So if you have, as you say, unpolarized incoming photons, you end up with unpolarized outgoing photons. So you get no polarization produced, right? So what happens is that in the last scattering surface, the microwave background actually sees different temperatures in different directions. And so if you have a so-called quadrupole, so you have colder photons coming from this side, hotter photons coming from this side, what you're looking at in the microwave background will have a net polarization in this direction. So now if you think about building up the microwave background, so if you know anything from, if you have any physics background at all, you know that we build everything from sine and cosine waves. So the polarization pattern from a sine wave looks like this, right? So from hot spots, it's seeing so an electron sitting here is seeing cold radiation from here, hot radiation from here, so the net polarization from this patch is going to be this way, and it alternates across, right? And then gravitational waves, they do this, but then as you sum these things up, So as you make density fluctuations by summing up plane waves, then the net patterns you get look like this. So it's coming from the fact that the temperature fluctuations, so it's scattering off an electron on the last scattering surface, and that electron is seeing a non-uniform radiation background. And so that it's projecting that into the polarization. Yeah.
So we have time for maybe one more question.
You've asked a lot. Let me take someone else. Yes.
Shouldn't B-modes be unreliable because of the different quantum fluctuations at the beginning of the universe? Since it was so compact, we could have increased them on a larger scale.
I'm sorry, I didn't catch the question.
Shouldn't the B-modes be unreliable because they could have been imprinted by quantum fluctuations when the universe was very small?
Yes. Well, so they are. So let me say they are imprinted by quantum fluctuations. So it is the quantum fluctuations of space-time itself that are the gravitational waves. But the B modes, so essentially we only see the only thing that's important is the last time the photon's scattered, right? And that's right at the last scattering surface. So the only thing that's important for the polarization is the very last time they scattered. And so all that information is imprinted on that last scattering surface. So it's the presence of gravitational radiation, gravitational waves, at the last scattering surface, which imprints this polarization. So, yeah.
So
all right.
You can come down again to ask more questions, but let's thank Peter for